Okay, so those notes on homework, it's due on Tuesday. So get working on that. Don't wait till the last minute, even though it seems like it should be easy because you get the property values already up front. It's not going to be specifically very easy. So make sure that you start it with plenty of time so that you can understand it, because that will help you on the exams as well. So today we're moving out of chapter 10. We're done with the gas power cycles, we're done with the vapor power cycles, and we're moving into chapter 11 where we're talking about compression cycles. So rather than producing work or generating electricity, we're actually going to be using work and electricity to transfer heat opposite to its natural flow. So we're going back to talk about refrigerators and heat pumps, which we talked about in chapter 5, but we're going to look at them in more depth. We're going to look at the actual cycles, we're going to analyze the steady flow engineering devices separately instead of just looking at the broad overview of a refrigerator or a heat pump. So we're going to talk a little bit about the different cycles that we can use, and we're also going to look a little bit closer at what changes to those cycles might do to our coefficient of performance and things like that. And then we're also, in the next lecture, going to look at the second law analysis, so determining the exergy destruction using refrigerators and heat pumps and things like that. So it's kind of fun. So as mentioned previously, last chapter was all about power cycles. We're talking about the vapor power cycle in the Rankine cycle, or we were talking about the gas power cycle, which is the Brayton cycle. But now we're talking about something that instead of generating a workable, generating work or a usable force or any kind of a power output, we have to put power into it in order to transfer heat opposite to the way that it wants to go. So heat engines, they're all kind of the same if you look at it from the grand overview. You have a heat input, a work output, and a heat rejection process. Okay, the same goes for refrigeration cycles or vapor compression cycles, often just simply called refrigeration cycles because regardless of whether it's a refrigerator or a heat pump, you analyze them exactly the same. It's just your desired output is different. Okay, I'm burning up in here. Does anybody else want to prop open the doors? The air's not turning on. I don't know why. But it's hot. Maybe that'll work. I'll see. So these compression cycles are also operating between this high and the low temperature reservoir, but our desired outcome is different. So whether it's a heat pump, where we're trying to heat up a home, so we're taking latent heat from the outside and putting it into our house through the magic of thermodynamics, or a refrigerator where we're taking a cold space and making it colder by removing heat from that space and depositing it into the air within our home or within our kitchen. So these compression cycles require work in order to reverse this flow of heat transfer, because otherwise we would be violating the second law of thermodynamics, right? So energy has a directional quality to it. We can't just arbitrarily transfer heat in any direction we want. If we go opposite to nature or in the direction of decreasing entropy, it requires work in order to do that. So refrigerators, as mentioned, are to remove heat from a cold space to make it colder. And the desired output is what we're referring to when we look at the coefficient of performance. So our desired output, even though it's actually sort of like a removal, is that we remove heat from the cold space. So Q sub L is what we're concerned about, and then Q sub H is a byproduct of that process. So it requires a certain amount of work to move Q sub L. And then heat pumps, our desired output is to make the warm space warmer. So Q sub H is our desired output, and Q sub L is how much energy we need to remove from the environment in order to make Q sub H happen. So we also have a network input, again, to reverse the flow contrary to its natural direction. So if we look at all those three side by side, a heat engine, heat pump, and a refrigerator, we can see that for heat engines, when we look at the thermal efficiency versus the coefficient of performance for refrigerators and heat pumps, that all of the terms are kind of similar and the same. We've got work, we've got heat, we've got all of these energy terms that are coming into play looking at it from the grand overview, but the order is very important. So for a heat engine, work is our output, a net work output is our desired output, whereas for a refrigerator, Q sub L is our desired outcome. And a coefficient of performance can be and should be, and for a heat pump always will be, greater than 1. Whereas for thermal efficiency, it always has to be less than 1. So refrigerators and heat pumps both are operating on what's called the vapor compression cycle, not power cycle. Sorry, let me fix that real quick. Vapor compression cycle, and then the working fluid is always a refrigerant. So it's very difficult, and I can't think of any examples of water being used as the fluid for a refrigeration cycle. It just really wouldn't work very well because we need to have certain conditions in order to be able to transfer heat and in and out of that fluid at certain pressures. And so a heat pump operating under the same conditions as a refrigerator will have a greater coefficient of performance, meaning that if Q sub L and Q sub H and the work net in are the same values, if you're using that device as a heat pump rather than a refrigerator, it will be more effective. So this is because the terms from your work input and your heat input add to give you a net heat output that's greater than the amount that you're removing from the environment. So all things equal, heat pumps are more effective than refrigerators at being heat pumps than refrigerators are at being refrigerators. And when we're looking at cooling capacity or the ability for something to remove heat from another space, we are often given this value in terms of tons of refrigeration. So this is analogous to when we're looking at a heat engine and we're looking at the combustion part of the process. Fuel has a heating value associated with it. So how many tons of fuel do you need to burn in order for this process to occur? Well, when we're looking at refrigeration, this isn't how many tons of refrigerant we use, but this unit of tons of refrigeration is if we had 1 ton of water, and it's a English ton, not a metric ton, 1 ton of water, 2,000 pound mass of water, and we had 24 hours to freeze it completely, that would be 1 ton of refrigeration. So it's the amount of time it takes, or the amount of energy per time it takes to freeze 1 ton of water in 24 hours. Okay, so the unit equivalent of that is about 211 kilojoules per minute, or 200 BTUs per minute. Now, it's a little bit confusing to me why it's 211 kilojoules, because if you do the math on it, the latent heat of fusion for water is 334 kilojoules per kilogram. So that's how much energy per kilogram you have to put into water, remove from water in order to take it from a liquid to a solid. So liquid water at 0 Celsius, almost freezing, you'd have to remove 334 kilojoules of heat per kilogram of water in order to make it freeze. That's what that means. So if we look at the rate of this, 1 ton in 24 hours, we can convert tons to kilograms and then convert hours to minutes. So we get this rate of 907.185 kilograms per 1440 minutes. And then if we multiply that by the latent heat of fusion, it's actually 210.4 kilojoules per minute. So 211, they're rounding up, I don't know. But everywhere I have ever seen it, it's always 211. So take that as you will. But that's where it comes from. That's how they do the conversion, sort of. Okay, we know about the Carnot cycle. We've talked about it a lot in this class. It's the most perfect, ideal, reversible cycle. Its diagram is a little square on a TS diagram, so we like it. It's easy to analyze. It consists of 4 processes. 2 of them are isothermal and 2 of them are isentropic. So it's nice. It looks good. And if we look at the reverse Carnot cycle, we can use that as a model for a heat pump or a refrigerator. So the Carnot cycle operating in the opposite direction is a reversible heat engine, but if we reverse the arrows and go the opposite way with a work input instead of a work output, then we can use it as a model for a refrigerator or a heat pump. However, you will notice, hopefully, as was the case with the power cycle, that the Carnot cycle really doesn't work so well. Because from state 1 to 2, isothermal heat addition, that's fairly easy to do. We're operating under the dome. We can be on a line of constant pressure, add heat, and go from state 1 to 2 isothermally. Fairly easy because it's an evaporation process. But from state 2 to 3, isentropic compression, and states 3 to 4 and 4 to 1, they're a little bit more difficult to control. 3 to 4 because it's hard to go exactly from a saturated vapor to a saturated liquid and be that precise about it. And then also it's very difficult to compress a two-phase mixture. So if we're operating under the dome between states 2 and 3, we can either use a pump or a compressor, but if we have a liquid vapor mixture, the pump's not going to work very well and the compressor's not going to work very well, so that's not an ideal process. And then similarly, if we use a turbine from state 4 to 1, we've really got a lot of liquid in there mixed with our vapor, so it's not an ideal way to utilize this process either. So why do we care about the Carnot cycle? It's always that benchmark that we measure everything else against, because it's a completely reversible cycle, totally reversible cycle. Every stage of the process is internally and externally reversible. So we use it as the best case scenario. So again, if we compare our actual refrigerator or our actual heat pump to the reversible one, we can see how close we are to being ideal, or how far away we are from being ideal. So that's always the reason why we use the Carnot cycle and throw it in there. So an ideal vapor compression cycle that's not the Carnot cycle, similar to what we had to do with the Rankine cycle, is rather than operating in a perfect square where we're under the dome for the entire portion of it, we're going to have to take a voyage into the superheated region so that we don't have too much liquid in certain parts of our process, or two-phase compression or liquid and vapor if we were to put a turbine in there. So we can do a couple of things. One, we can still use the turbine, or we can replace state 4 to 1 with, or state 3 to 4, sorry, with a throttling device. So rather than having a turbine there and trying to keep it be some isentropic process, we can replace it with an isenthalpic process, or constant enthalpy process. So we still get that same pressure drop, but instead of worrying about two phases within a turbine, we can get the pressure drop with no work output by just using that throttling valve. So this is the basic cycle that's used for refrigerators, for air conditioners, for heat pumps, any of these vapor compression cycles that you see. This is sort of the idealized model that they're all based upon. If you were to go to your home and look at your heat pump outside, you would see these various components. The compressor is usually just right there outside. The evaporator and the condenser, they switch. Whether you're using it in the fall or the summer, the evaporator becomes the condenser and the condenser becomes the evaporator. So it's all in that nice little area right outside. The expansion valve sometimes is inside. So when we look at this ideal cycle, we can see on the TS diagram that now we are no longer operating completely under the dome. At state 2, here, we're up in the superheated region. So this is at the end of our compression process where we have this work in, but we're still operating from 2 to 3 along a line of constant pressure, and from 4 to 1 along a line of constant pressure. So these two processes are still isobaric, which is a good thing for us. But now instead of state 3 to 4 being an isentropic process, it's an isenthalpic process. So from 3 to 4, the enthalpy is constant, but the entropy is not. And in fact, the entropy will increase. It's also useful to look at this on pH diagram, which shows pressure with enthalpy, because we can see this constant enthalpy process and these constant pressure processes, and then we just have from state 1 to 2, which is a constant entropy process, is a little bit different looking. But it's another way for us to analyze and look at our enthalpy values, so we can see this distance here, how much energy input is required to go from 4 to 1. So we can look at that at a glance on the enthalpy diagram. And then from 2 to 3, how much enthalpy we are actually saving by throttling oh no, that's not the throttle process, that's the heat removal process. How much heat we're removing from 3 to 4, we can see that we're saving energy by not, or we're saving efficiency in this way, because it's a constant enthalpy process. Okay, so our coefficient of performance can be written in terms of the enthalpy values. And a good thing to note or to remember is that we'll improve that coefficient of performance for a refrigerator when we increase Q sub L or decrease work net, and for the heat pump if we increase Q sub H or decrease work net. And another way of thinking about that is increasing T sub H and decreasing T sub L. That if we decrease T sub L, Q sub L will increase, and vice versa. So let's do an example of this. So we're fortunate, I think, in this chapter that the problems are a little bit easier, but don't get overly confident because things will start getting difficult again soon. Don't worry. Don't you worry. Okay, so we have an ideal refrigeration process using R134A as the working fluid, which is convenient because we have tables for that in the back of the book in case you've forgotten. I've used them for a while. It's operating on this ideal vapor compression cycle between 0.14 megapascals and 0.8 megapascals. We are given the mass flow rate of 0.05 kilograms per second. So we need to find the rate of heat removal from the refrigerated space, the power input to the compressor, the rate of heat rejection to the environment, and then the coefficient of performance of the refrigerator. So let's talk about these quantities that we need to find. So A, the heat removal from the refrigerated space, what is that? What are they talking about? What term?
What, Q loss?
Q dot L. Don't call it loss, because it's L is for load, not loss. But yes, it's Q dot L. So what is Q dot L in terms of properties?
It's the area under the 1 minus 4A.
Okay, so the mass flow rate, because it's a Q dot, times H1 minus H4, right? Okay, part B, what are we trying to find? The work in. So W dot in, which is what? M dot times H2 minus H1. Okay, part C, the rate of heat rejection.
QH.
Q
Dot
H, right? Because it's a rate, which is equal to M dot times what? H2 minus H3. And part D, the coefficient of performance for a refrigerator is equal to what?
Q dot L over W dot N.
Yeah, Q dot L over W dot N. So it'll be in terms of H2, H1, and H4. Okay, so let's go through and find these property values. So state 1, what do we know about state 1? In the ideal case, do we have enough information to set state 1? Speak louder, I'm half deaf.
So it's saturated vapor.
Okay, it's a saturated vapor, and you know that because it's right on that line there, and it's also part of the definition of the ideal vapor compression cycle is that it comes out as a saturated vapor before it goes into the compressor. So X is equal to 1. What else do we know?
0.14.
So P1 is equal to 0.14 megapascals, which is 140 kilopascals. So we go to our tables. Where are the tables for R134A? After water. What table do we need to look at? No, not that high. Not 20-something.
A12.
A12. And why A12 and not A11?
Because it's given in terms of pressure, not temperature.
That's right. So A12 is in terms of pressure rather than temperature. I've already converted to kilopascals. So what values do we read off of that table? What values do we need? H1. How do I find it? Okay, it's H sub G at 180 kilopascals. So that value is what? 180? No, 140. 239.19 kilopascal, kilojoules per kilogram, right? So 239.19 kilojoules per kilogram. Is there anything else we need to look up at state one?
So how do you know you said the HG? How do you know to do that?
How do you know, Blake?
It's a saturated vapor.
How do you know, Chris?
Because the X is equal to 1, so that means it's saturated vapor. So the subscript G on the table is a saturated vapor.
And what's subscript F?
Saturated liquid.
Saturated liquid, right?
State one's on the right-hand side of that dome right there.
So when X is equal to 0, then we use the H sub F. When X is equal to 1, we use H sub G. If X is equal to somewhere in between 0 and 1, we need to know what X is. And we do H sub F plus X times HF.
So does that mean our next fully defined state that we have would be state 3?
Yes, state 3 is fully defined. But before we go to state 3, let's stop at state 1 for a minute and think if there's any other property values we need to look up while we're there.
Entropy.
We'll need entropy, and why will we need that?
Isotropic.
Yep, it's an isentropic compressor, so this process from 1 to 2 is a constant entropy process. So once we fix state 1, we know that the entropy of state 2 will be equal to S1, right? And we know the pressure at state 2 and the entropy at state 2, then we now have 2 independent intensive variables to look it up. Okay, so S1 is equal to 0.94467 kilojoules per kilogram. Oh,
So on one side, it'll be isentropic now, but going from the 1G states, it's still isentropic.
yeah, from 1 to 2 is isentropic. Because we're still working with the ideal process. Never fear, we will get to actual processes where it won't be isentropic, so you can see how that goes. So state 3 is fully defined. What do we know about state 3? X is equal to 0, and the pressure at state 3 is what? 800 kilopascals. So Blake, when X is equal to 0, where do we look up our values?
The HF.
H sub F, that's right. So H3 is equal to 95.48 kilojoules per kilogram.
So like I was asking him, even if like 3 is on the line, then it's still quality of 0?
The line is
The only
0.
place it's 0.
Yeah.
On the left-hand side is the only place it's 0. On the right-hand side is the only place it's 1. In between, it's a value between 0 and 1.
So what if 3 is floating off into space to the left of the curve?
It would
If
be
we're over here,
compressed.
then it's a compressed liquid. You know this stuff.
I didn't know that.
You did know this. Come on. We did that all last semester.
And then if where 2 is off to the right, it's a superheated vapor.
That's why we're always talking about under the dome, X is between 0 and 1. On the line
So,
here is
so then
0.
when it's in the left, like that random dot there, is it use the compressed liquid tables?
If you have a pressure value for it. If you don't have a pressure value,
You have to do the.
then you just make the compressed liquid approximation and you assume, well, it's not on the line, but we're just going to jump over to the line and use the temperature that it is to look it up in the tables.
And then the same instance for the far right, if it's far past the line, it's superheated?
Yeah.
Okay.
But we have plenty of tables for superheated vapors. It's just the compressed liquid region, we don't have tables for this, but there's one table. And it starts at 10 megapascals or something like that, 85. Okay, going back to this where were we? State 3. Okay, so we found the enthalpy at state 3. Now that we know the enthalpy at state 3, what else does it tell us? Cody said it earlier. Now we know state 4. Why? It's an isenthalpic process. So if we look at a valve, H is equal to H. So let's say this is H3 and H4. That the pressure decreases, but the enthalpy remains the same. So that's why we like valves, because we're able to get a pressure drop without utilizing any work. It's a simplified solution to the problem. And then it makes analysis easy because the enthalpy remains the same. So H4 is equal to 95.48 kilojoules per kilogram also. But what about state 2? Okay, superheated. We know the pressure and we know the enthalpy is the same as state 1. So we have to go to table A6, right? No.
A13.
Because we're in R134A, A13. So we go to table A13, we look it up, and we find that our enthalpy at state 2 is equal to 275.40 kilojoules per kilogram. And we have to interpolate using the entropy. Okay, this is all stuff we've done all semester. We should know how to do this. Okay, so now we can just go through and start plugging in numbers to our equations. So we know H1, H4, H2, H1, H2, H3, and then we'll calculate that. So if we put in the numbers for this, we get 7.19 kilowatts, 1.81 kilowatts, 9.00 kilowatts, which incidentally, if you notice, Q sub H is 9 kilowatts. If we were to do an energy balance on this whole thing, we would find out that work in is equal to Q sub H minus Q sub L. Nope, opposite, sorry. Q sub L minus Q sub H. So the math checks out on that, fortunately. And then our coefficient of performance we calculate to be 3.97. So we've done A, B, C, D. The hardest part was finding state 2. Everything else is easy. Okay, so now, what if, instead of using a valve here, or a flow restrictor, we put in a turbine. We somehow have a turbine that's not affected by moisture flowing through it, that we designed it such that it's okay. And the flow rates are low enough that it's not going to cause any real damage. So now instead of going in a constant enthalpy process, we are going to follow a constant entropy process. How does it change our analysis?
You'll have to find the quality of state 4 because it's a mixture with the engines there. You'll have to find the values at 140 kilopascals.
Okay. Did you have that same comment, Lynn?
No. How do we know there's a valve from 3 to 4?
Because it told us in the problem description that it's an ideal vapor compression cycle and that has a valve there. Plus the picture shows us that it's along a line of constant enthalpy on the TS diagram.
So you have to assume ideal vapor compression is a valve?
Well,
That was on the slide before, when we learned about ideal vapor compression cycles. There, this is what we're looking at.
Oh, okay.
So that would also give us a network out if we used a turbine.
Oh,
We could
interesting.
Apply that back to the compressor.
Right, so we're going to have some network out that we can potentially use to power our compressor, or part of our compressor. Probably it's not going to be enough to power the whole compressor. So we need to find our new state 4. So instead of going here, we're going here, this 4 prime on the picture. So this 4S here. So let's do that. Let's replace the throttling valve with the turbine, and we'll do the new analysis. So state 1 doesn't change, right? Our H1 is still 239.19 kilojoules per kilogram. And our entropy is still the same. S1 is 0.9446, 7 kilojoules per kilogram. State 2, still isentropic. H2 is the same, 275.4, 0 kilojoules per kilogram. State 3 doesn't change, it's still the same. H3 is 95.48 kilojoules per kilogram. But now we have to look up S3 at this state 3, which is S sub G. Does anybody know what that value is? So S sub G at 800 kilopascals. No, S sub F, sorry, S sub F.
0.35408.
Yep, 0.35408 kilojoules per kilogram Kelvin. Okay, so then we use this to find state 4. So we're going to have to calculate quality, blah, 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 blah. We find H4 is equal to 88.95 kilojoules per kilogram. Okay, so what was it before? 95.48. We've decreased our enthalpy to 88.95. Okay, so now we have two things that we need to calculate. One is now we have a workout term that we didn't have before. So what will be the equation for workout? Work dot out, power out. M dot, I know that, right? Where is the work occurring?
H4 minus H3.
It would be H3 minus H4. H4 isentropic, right? So this is H4 isentropic. So we can calculate that, and we find that it's 0.33 kilowatts. How much was our work in? Do you remember before? It was 1.81 kilowatts. Ugh. Kilowatts. So now our net work in is going to be work in, actually power in, minus work dot out. So we find that we now have reduced our power consumption to 1.48 kilowatts by adding that turbine. So we can calculate our new coefficient of performance for this refrigerator. So our Q sub L term stays the same. Net. Q sub L is the same at 7.19 kilowatts. No, it's not. It's not the same. I mean, it is 7.19, but it's different. So Q dot L is equal to H1 minus H4 times M dot 7.19 kilowatts. That one changed also. So anything that relies on state 4 will change. Q dot L changes, and this work out changes, and our coefficient of performance will now change. So it's 7.19 kilowatts.
We got 7.19 kilowatts for part A.
7.51, sorry.
So not only do we reduce our required work input, but we also are getting a higher transfer rate from.
Yes. Okay, so 7.51 kilowatts. Now I gotta make sure. Okay, this work in is wrong too. I was reading off the wrong part of my paper. So work in, oh, no, hold on. No, I did it right. Work in before was 1.81 kilowatts, that's the same. I'm going off script. Okay. So now we divide through by 1.48 kilowatts because that's our net work. So coefficient of performance is based on the net work input. We find our new coefficient of performance is 5.07. So that's compared to before was 3.97. So we've increased our coefficient of performance. We've increased the amount of heat we're removing from a refrigerated space. So we have to balance that out with how much it costs to implement a turbine, how much maintenance is required for using a turbine that has liquid and vapor flowing through it, and things like that. So although we get a bump in our coefficient of performance, sometimes it's not worth it. It significantly complicates the process, increases the amount of noise. Imagine if you had a turbine in your house associated with your heat pump. Instead of just a throttling valve, so your compressor's outside making noise and a turbine inside making noise. Probably not very many people would like that. So, something to consider. Okay, so actual vapor compression cycles, of course, differ from the idealized case. You'll never ever see an actual situation that is as good on paper as it is in real life. Is as good in real life as it is on paper. So we can't completely ignore the irreversibilities. We have to look at them, we have to take them into account, because we're always going to have fluid friction, and in particular with household refrigeration systems, your heat pump or your refrigerator, those are long, skinny, coiled pipes. There's lots of friction and lots of heat loss through these copper pipes. And so there's really a lot of irreversibility in the systems. We just have to somehow find a way to model it. So in the ideal case, the refrigerant will leave our evaporator as a saturated vapor. So ideally, we're right on this line here, but actually that's difficult to control. It's hard to make sure that you're operating specifically on the line, so you have to make a choice. Do you want to err on the side of being under the dome so that you could potentially put a two-phase mixture through your compressor? Or do you err on the side of being slightly superheated so that there's no chance of putting a liquid through your compressor? Okay? In most cases for engineering design, we err on the side that will be most beneficial to our equipment. So it's slightly superheated. And then in the ideal case, there's no pressure drop between the evaporator and the compressor, but in real life, there's going to be a long, thin tube that's connecting the refrigerant to those two components, and so the friction in those pipes can be significant. In the ideal case, our compression is isentropic and internally reversible, but in the real compression cases, it's always going to involve friction, and it's always going to involve some heat losses or heat transfer to the surroundings, and in some cases, it's heat being transferred into the compressor, depending on what environment it's operating in. And then the ideal case, the refrigerant will leave the condenser as a saturated liquid over here. But again, it's another one of those very difficult, precise phases to maintain. So we err on the side of being all liquid, so it will be slightly subcooled. So we're operating, instead of right on this line of the dome, we're going to be slightly superheated and slightly subcooled, because our equipment will operate better and function better if we're not operating in the two-phase region and we're staying either on the very edge of the dome or outside of it. But it ends up being the case that this offers us the opportunity to have greater heat transfer once we transfer, once we go through the isentropic device to the evaporator, because our enthalpy will be lower as a subcooled liquid, and because the enthalpy remains constant through that valve, then it will be a lower enthalpy before we get to our evaporator. So that means there's a greater potential to have an amount of heat absorbed or rejected depending on which side of the evaporator we're worried about. So let's do an example. And I love how they go through and they talk about the actual case, that there's all these losses and there's 8 different states. And then we say, well, we're still going to idealize the actual case because it's too complicated and difficult to analyze all the heat. loss in the pipes and the pressure drops in the condenser and all of this stuff. So it's an idealized actual case, but it's less ideal than the fully ideal case as we're looking at it. So we still have 4 states, and in this case, primarily, we're looking at states 1 and 3 not being on the line specifically. So it makes it just slightly more complicated to look up property values, but that's okay because we're good at looking up property values. So at state 2, or at state 1, we start off at 0.14 megapascals and negative 10 degrees Celsius. And we still have the same flow rate, so 0.05 kilograms per second. And then we leave the compressor at 0.8 megapascals and 50 Celsius. So we've increased the pressure, we've increased the temperature of our fluid by compressing it. Then the refrigerant is cooled in the condenser at 26 degrees Celsius and 0.72 megapascals. Once it leaves the condenser, it goes through the throttling device and the pressure is decreased further to 0.15 megapascals. So you notice here that they are accounting for a slight pressure drop from 0.15 megapascals to 0.14 megapascals through the condenser. Okay, the arrows are backwards, so it makes me confused when I try to think about it. Okay, so we need to figure out the rate of heat removal, the power input to the compressor, the isentropic efficiency, and the coefficient of performance. Now this is the evaporator, not the condenser. Okay, so let's start looking at property values. State 1, what is the state of our refrigerant at state 1? Where is it, Blake?
What, I'm sorry,
State 1, where are we?
say we're on this superheated,
Yeah, we're superheated. How do you know that?
because it's to the right of the dome.
Yeah, it's to the right of the dome, so we're outside of that line. State 1 is 0.14 megapascals and negative 10 degrees Celsius, so we can go where to look that up? Superheated tables for R134A, so what table is that?
I have a question, how is it superheated if it's negative 10 degrees Celsius?
Because it's a refrigerant. Because that's why we use refrigerants. They have different boiling and freezing points than water. So it can be negative 10 degrees Celsius but be a vapor. Yeah. Okay, so it's superheated vapor, table A13 for R134A. So if we go to that table and we look up the enthalpy value at state 1, we find that it is 246.37 kilojoules per kilogram. Okay, now what about state 2? What are the conditions of state 2?
This is
0.8 megapascals and 50 Celsius. Okay, it's still superheated, and we can know that just by looking at the picture, right? Before we even go to the tables, that it's superheated. So we go again to table A13, we look that up, and we find at 0.8 megapascals and 50 degrees Celsius that our enthalpy at state 2 is 286.71 kilojoules per kilogram. Okay, now state 3, what do we do?
Is it on the line?
I think it's also.
It's not on the line.
It's compressed.
It's a compressed liquid, so it's 0.72 megapascals and 26 degrees Celsius. How do we find the enthalpy of a compressed liquid when we don't even have a compressed liquid table for R134A?
The temperature
Okay, so we have to look, H is equal to H sub F at 26 degrees Celsius.
How much
Which-
error will that be with R134A?
I don't know. 7.83, can't read my own writing. Probably 0.83
Yeah, point.
kilojoules per kilogram. So an additional correction factor that we could make is we could say H is equal to H sub F at 26 degrees C plus the specific volume at V sub F at 26 degrees C times the pressure of state 3 minus the saturation pressure. So this will offer an additional correction factor that will get us even closer to the actual value. If this value is a very large value, then we know our percent error is going to be higher or greater. But in this case, 7.72 megapascals, whereas the saturation pressure at 26 degrees C is 685. So it's not that far, 720 versus 685. So it's pretty close.
Now, if that's like really far, like if that is a great difference, like if we see that the saturation pressure and our given pressure is pretty far away, you want us to use this correction factor?
Yeah. So like in the last homework on problem 2, homework 5, it was like 15 megapascals. Nobody used the correction factor. Very few people used the saturation or the compressed liquid table. They just used like the values from the regular table. So that led to a lot of errors in calculating that enthalpy at state. I think it was like state 2 or something. So be careful about that. Anytime you're in the compressed liquid region, do a second thought of, okay, number 1, when I'm looking up this enthalpy value, if I'm making the compressed liquid approximation, I need to use the temperature to look it up. Don't use the pressure. And if it's at a very high pressure compared to the approximation I'm making, then you'll need to add on that correction factor or see if there's a table. And in our book, there's not really tables. In real life, if you were using like Ease for another software that allows you to also calculate property values as you do your problems, then it would find the exact value. But we're always interpolating in between lines of the table anyway, so there's generally going to be some errors out there. Okay, where were we? We found state 1, state 2, state 3. What about state 4? What is state 4?
Saturated mixture.
Okay, it's a saturated mixture. How do we find the enthalpy there?
Use, because H3 is equal to H4.
Ding, ding, ding.
And
So
then
state 4, H3 is equal to H4 is equal to 87.83 kilojoules per kilogram. Okay, so we know H1, H2, H3, and H4. That should be enough for us to calculate the first 2 parts of this problem, part A and part B. But look at this part C, the isentropic efficiency of the compressor. Oh boy. What do we need to do in order to calculate an isentropic
We'll
efficiency?
have to find state 2S.
We're going to have to find the isentropic state 2, right? So state 2S is where S2 is equal to S1, which if we looked up S1, it's 0.9724 kilojoules per kilogram Kelvin. So we are able to look up H2S by going to the tables and interpolating using the entropy to find the H2S is equal to 284.20 kilojoules per kilogram. So the actual H2 is 286, our isentropic H2 is 284.2. And this is another good time to do a reality check to see if your value that you find or calculate for your isentropic state is wildly different or much lower, or, then you may want to go back and recalculate a few things.
So this is kind of like a reverse of like what we're used to doing, because normally we have the isentropic state and then finding the actual, but now it's doing actual, like going back to
given the actual state, which is kind of nice, because at first you're like, oh, sweet, they give us the pressure and the temperature, all I have to do is look it up. But then you have to back out and calculate the isentropic case, so we can calculate the efficiency. So let's just get a clean slide and do that. So part A, we're finding Q dot L, which is equal to what? H1 minus H4. So if we plug in the numbers for that, we get 7.93 kilowatts. Okay, so now remember, this is the actual case. In the ideal case with the throttling device, we got 7.19 kilowatts. And the ideal case with the turbine, we got 7.51 kilowatts. So we're comparing here. We'll talk about those in a minute. So part B, the power input to the compressor is equal to what?
Minus H1.
H2 minus H1. Is it H2 actual or H2S? H2 actual. So that's equal to 2.02 kilowatts, which if we compare to 1.81 and 1.48 kilowatts from before. Part C, our isentropic efficiency for the compressor. What is that equation?
Is it work actual over work isentropic?
Which one is going to be higher? For a compressor. Which case will require the greatest work? Okay, so the actual case will be higher. So it has to go on the bottom, right? Because our efficiency can't be greater than 1. So it's our work isentropic over our work actual for the compressor. And if you can't remember how the enthalpies go in these equations, just always think about that. Okay, which one is going to be a larger value, right? For a compressor, because it's a work input, you're going to require more work input for a less efficient device, right? So it has to go on the bottom. All right, and if you ever calculate an isentropic efficiency and you get a value greater than 1, go back and redo it because something's wrong. Okay, so our isentropic work, what is the equation for that? And we don't have to put in m dot because m dot's the same, it'll cancel out. We just need enthalpies now.
H2S minus H1 over H2A minus H1.
That's right. Okay, so we already calculated this H2A minus H1. We can find that our isentropic work is equal to 284.2 minus 246.37. Will someone calculate that for me? 286.71 minus 246.37. So our efficiency ends up being 93.8%. But let's just look at it, because our actual work is 202 kilowatts. What was our isentropic work? This top line.
So 37.83 kilojoules per kilogram. What's our m dot?
0.05.
1.8915.
Okay, so our isentropic work would have been 1.8915 in this case. Okay, so our efficiency is 93.8%, which is pretty decent. That's not too bad, not too far off from isentropic. So now our coefficient of performance for the refrigerator, again, is equal to Q dot L over work dot in. We calculated QL and work in, so it's just 7.93 kilowatts divided by 2.02 kilowatts, which gives us 3.93 for our coefficient of performance. So we can compare that again to the case with our throttling valve where we have an isentropic compressor, and 5.07 was when we have the turbine involved. So we're not too far off. The property values have changed slightly. I've changed some. But fortunately for us, even if we're operating under less than ideal circumstances, we can still achieve fairly good heat transfer rates to remove heat from a space without losing too much benefit from that. Because we're already using work to move heat and, we're generating lots of entropy. We'll talk about that later. Yes?
If you know Q.H, would you use the 2S or 2A?
For Q.H?
Yeah, just hypothetically.
Yeah, so if you want to look at your actual case, you'd have to use the 2A.
Okay, so it would probably be stated, which one.
Yeah, you'd have to know
Okay.
which situation you're looking at. But in this case, since we're dealing with an actual vapor compression cycle, if we want to calculate Q.H, it would be H3, let's see, Q.H is now H2 minus H3 times M dot. And we use the actual A. Okay, any other questions on this example? Okay, so again, get started on your homework. Make sure that you reference back to homework 5 using the solution that's already online. Use the correct property values to get started. And make sure you use actual property values, not isentropic property values. So you have to dig through all of my writing to figure out which ones to use. And don't leave these till the last minute because they can be somewhat involved. Ones. And I've thrown some tricks in there, so it's different than the examples that I gave last time.